Alright, in our previous video we defined curvature to be, well, we found out a nice way to calculate curvature, which was to find the magnitude of t prime of t over the magnitude of r prime of t. So the magnitude of the unit tangent vector divided by the magnitude of the derivative of our position vector in there. What we want to find out in practice is that that's a little bit difficult to compute, and so there's a couple of other ways that are a little bit easier. One way is that it's r double prime of t cross r prime of t, the magnitude of that, divided by the magnitude of r prime of t raised to the third power. That's a great way to do it if you've got vectors. And if you actually have a function, if you've got y equals f of x, you can do your curvature by doing the absolute value. Now we're into absolute values because we're just talking about regular old functions again. It's the absolute value, not the magnitude. Well, the absolute value is magnitude in 2 dimensions. Excuse me. Divided by 1 plus f prime of x squared, and that whole thing raised to the 3/2 power. It's kind of a messy formula, but it works. It gives us the answer. So that's the good thing there. Let's look at using an example with this, maybe the second formula. Let's take our function r of t. Ooh, I didn't mean to do that. R of t is equal to t squared, natural log of t times the natural log of t. And I want to find the curvature at t equals 1. Find the curvature at t equals 1. Alright, and I'm going to use this second formula this time. So to use that second formula, I need the first derivative and the second derivative of that. So I need r prime of t. R prime derivative of t squared is just 2t. The derivative of natural log of t is 1 over t. T times the natural log, I got to use the chain rule. So it's going to be the first one times the derivative of the second plus the derivative of the first times the second. So that looks like it's just 2t, 1 over t, and 1 plus the natural log of t is my r prime. And then I need r double prime of t. And that would be, well, derivative of that's going to be 2. Derivative of 2t is going to be t. Here you've got t to the minus 1. The derivative of that is going to be minus 1 t to the minus 2. The derivative of 1 plus the natural log of t is going to be 1 over t. Alright, those are all the pieces I need. And the nice thing about it is we're trying to find it at a specific point. So I can find out what those actual points are. Let's find out what our vectors are. What is r prime of 1? If I plug in 1 for t, I'm looking at the vector 2, 1, and 1 plus the natural log of 1. The natural log of 1 is 0. So it's 2, 1, 1. And r double prime of t would be 2, negative 1, and positive 1. And so to find the curvature, I want to do r1 cross, or r prime cross r double prime. Actually, it's r double prime cross r prime. These are all vector functions. So I want to do that cross product of 2 minus 1, 1 crossed with 2, 1, 1. And that's going to give us, let's see, the I component is going to be minus 1 plus 1. The I component's going to be 0, I, minus the j component. I want to do 2 times 1. 2 times 1, that's a 2 times 1 there. 2 times 1 minus 2 times 1. And that's going to be 0 as well. And then the k component will be 2. And then that other diagonal is going to be a minus 2. So 2, but I got to subtract a negative 2k. So that looks like it is just 0, 0, 4. And the magnitude of that, guess what the magnitude of that is? That's just going to be 4. So the curvature is going to be 4 divided by the magnitude of r prime raised to the third power. So the magnitude of r prime raised to the third power. So that's going to be the square root of 2 squared plus 1 squared plus 1 squared, all raised to the third power. So our curvature will be 4 over the square root of 4, 5, 6, square root of 6 cubed. We can simplify that some if you want, just for fun. So 4 over, that's root 6 times root 6 times root 6. So it's 4 over 6 root 6, which is 2 over 3 root 6. And I think that's about as simplified as we can get. We didn't rationalize the denominator, but that's okay. I'm okay with that there. So 2 over 3 root 6. So that would give us the curvature at that point. What that means on our curve is that if we've got our curve going along here, if we add in an osculating circle, if we were to draw a circle that just touches at that point, the radius of this circle, where it's tangent to that curve, right at that point, the radius would be 1 over the curvature. It's going to be 3 root 6 over 2. And that would be the osculating circle, the circle that just is tangent, just matches the curvature of that circle, of that graph at that point. All right, I'm going to find some, well, let's just leave it there. Thank you.